Okay, so in this second part of the tutorial, what we will do is to choose our particles. So we can see how the micrographs look like. So this is the appearance of our micrographs, and then we have to choose which are the particles we are interested in. So in this case, all these blobs or all these circles are the ones we are interested in. Okay, so then we will use different programs for that. So one of them is well, all these programs are here. So by the way, I forgot to tell you which are the which is the menu for the CTF estimation. So you can see it there, and there are pre-processing steps like these pre-processed micrographs that can take invert the contrast, can denoise, can apply Gaussian filter. So you can be very creative there in your workflow. And then what we will do here is particle picking and 2D classification. So for that, for the picking, you have here all these operations. So you have many pickers, and also, each one of them has a different rationale. So some of them, they try to find objects of a given size. Some others, they have been trained with previous data sets, so they know more or less how a particle looks like. That is the case of Crayola or any one of the deep learning algorithms. Some others, they try to pick particles that look like a template. These are less and less in fashion, but if you have images that, for instance, you have or you process ribosomes with different factors, and then you may use previous examples of your previous samples from your ribosome with another ligand, and then use those images of the ribosome to pick in the new micrographs. But nowadays I would say this is not really much needed. And then, for instance, XMIP, it has two phases. One is manual, where you teach the algorithm what you are trying to look for, and then the algorithm is learning from you, and then it applies to the whole data set. So here I have used 4 of them, and the reason for that is that different pickers, they have different properties and different errors. So for instance, here we can see that many of the particles are off-centered, and some of them, they are in the middle of the eyes, and it is not a particular criticism to this particular picker. It is all the pickers make errors, and some of them are more obvious than others. So for instance, here we have like 4,000 particles. Here in this case we have 6,000 particles, so we would expect in this particular case to have more errors. We can see that really they overlap too much, and very often they are in the middle of the eyes, and some of the particles, they are also correctly picked, but not all of them. And then we have, for instance, Crayola has 4,000 too, and this is one of them that has been trained on previous datasets, and you still see that it makes errors. So there is no algorithm that is error free. And then manual XMIP manual automatic picking, it starts with an with a manual training, and so you see that we have used all these for training, and then these are the automatic pickings, and again it is missing some of the particles, some of them are incorrectly picked, some of them are in the middle, and there is no algorithm that is absolutely error free. So actually, depending on the data set, but there could be an estimate that the amount of missed particles could be somewhere between 10 to 30%, and the number of incorrectly identified coordinates can also go from 5% to 30-40% depending on the data set. Okay, so but the point is that having all of these integrated into a single place allows you to compute consensus. And so all this consensus is, okay, so now we have an algorithm that will look at the outputs of all these pickers, and they will and this algorithm will try to find the commonalities of the pickings. So actually we didn't get into that, but the main parameter in each one of the pickers, typically the most important one, is the size of what you are trying to pick. And for that, what you can do is to open, for instance, let's open this one. This is the manual picking of XMIP, and you have here the particles. So here is a box of 100. So let's see with 300. So we see that 300 nicely fits. And there is always a debate what should be the box size for picking. So I would say, but this is again a personal view, I would say a box size that is tied to the particle lets the algorithm understand what you are picking, and actually it will learn whatever you teach. So if you teach that the box is tied to the particle, it learns that. If you teach that the box size is something big and the particle should be isolated inside, it also learns that. So I prefer picking with tight boxes, and then later at the 3D reconstruction, it is true that we have to enlarge the box size so that we can correct for the CDF in a better way. But otherwise, this is good for picking. So 300s we said. So let's forget about this box. We don't need it. Actually, this was just to show you how to choose the box size. So we can delete this one. Okay, so and that is the main parameter, and then each one of the algorithms have their own particularities. So for instance, what is some filters, and what is the maximum resolution to consider, some thresholds, but those are very particular to each one of the algorithms, and by fine-tuning them, probably you can get a better picking result in that algorithm. And then here you have this deep consensus. So this deep consensus will take the output of different pickers, and then we will construct a new model, deep learning model on these inputs, and the rest of parameters normally they are not important. There is one that is again, you don't have to choose, but it is important to understand that it is doing that. So beside the points or the particles that you are given, the algorithm has access to a data set of incorrectly picked particles. So those are contaminations, those are blobs, ice crystals, or whatever could be in the micrograph. So beside what you think it is a particle, it has also access to what is not really a particle. And then it will produce something that, for instance, we can see the deep score histogram. So no, this is not histogram, the histogram is here. So this is the histogram of the scores assigned to each one of the coordinates. So it goes from 0 to 1. 0 means the algorithm is pretty sure that that is not a particle, and 1, the algorithm is sure that that is a particle, or at least something inside. So here we see all the Apoferritins. Here we see mostly empty regions or regions where we have carbon edges or whatever. And then also, so you can try to choose your threshold here. So threshold of 0.5 has some theoretical meaning, but sometimes it is not the best threshold. So you can go to 0.5, see how particles look like there. So for instance here we see 0.5 is here, and we have some off-center particles, and you may you may want to keep them or not, depends on you. And also something that I find useful is to make a plot of the sorted set score. And then for instance you see here that there are 15,000 particles, and then there is a point at which this curve starts to decay, and then you may choose this corner here. So sometimes the corner is very useful. Sometimes you may go directly for the 0.5, and then you will remove you will remove all these off-center particles later, or you will recenter them or whatever. So I will do that in this case. So I have taken the 0.5. You can do that by, for instance, you go to 0.5. So you go to 0.5, that is here, and then select to here. So all these particles have now been selected, and now right click and disable, and then you produce a new set of coordinates. That is actually what I did, and then I created a subset that I call it subset of 0.5 with 4,000 particles, and then you can go for the further cleaning. So if you look at these coordinates, now they are not so terrible. Some of them are duplicated because there is a minimum distance that if two coordinates are closer than this minimum distance, then they are considered to be the same particle, and the minimum distance is typically 10% of the box size, and this must be further than this 10%. But otherwise, we can see that the particle selection after the deep consensus is not terrible. It is actually pretty good. And yeah, so we can see, for instance, here we see the carbon edge, and none of the particles is on the carbon edge, but also most of the particles that look like kind of too thick. The ice here is probably too thick, and what we are seeing is multiple layers of particles, so they have not been selected either. But still, it is a good thing to use some algorithm that has been specifically trained to remove particles on the edges and on contaminations, aggregations. This is this micrograph cleaner. The input of the micrograph cleaner is simply the set of coordinates, and then after running, what you will have is an output that gives you what is the score assigned to each one of the particles, and this score we see that most of them are below 0.97, and then what we can do is just put here 0.97. Then we look at the particles, we look at the coordinates, and create a new set of coordinates with that threshold. That is what I did. And then here we have two outputs. One is the full size with all the same number of coordinates as the input, but now with this new score. And then after choosing those that are below or above, 0.97. So again, we can look at the coordinates just to see how they look like, and probably they are almost the same as the previous one, except for a few, like 1% of the coordinates have been dropped. And then the next step will be to extract these particles. So now there is an extra particle extraction. You may see that the number of coordinates are not exactly the same as the set, as the output set. The reason is that some of the coordinates have been discarded, probably because they are too close to the border of the micrograph, and when extracting, there is no space for extract the full box size. And the main parameter here is the set of coordinates. So which are the set of coordinates, which is the CTF. So you attach the CTF at this point. So from this point on, all these particles will have a CTF that is the one that you assign here. So here I have chosen the triple consensus between GCTF, CTF-find4, and XMIP. And for the 2D analysis, typically you don't need big images. We will not do high resolution classes. So all we want is just to make to understand what is the kind of particles that we have. If we have a mixture, to get rid of those particles that have escaped these all these particle pickers and filters of deep learning, micrograph cleaner, and so on. And then the other important parameters is whether you want to invert the contrast, do phase flip. So in the old versions of XMIP we needed the phase flip particles. This is no longer the case. So now most of the programs like XMIP, Relion, CryoSpark, they can work with non-phase flip particles, and some of them they cannot even work with phase flipped. So XMIP and Relion, for instance, they can work either with phase flip or with non-phase flip images, but CryoSpark I think they cannot, for instance. And then the normalization. Normalization is something that you need, and that is trying to make all the numerical values to be somehow consistent with each other. Okay, so now we have these particles here, and we can look at what is the, for instance, the average and standard deviation images. So this is the average, and it should look like our particles. And the standard deviation, we see that most of the differences are either inside or outside the main part of the Apoferritin. And then we go for a first round of 2D classification. So I have used here CryoSpark 2 because it is really fast, and then we can see the particles with Scipion. You can also see it in the GUI of CryoSpark, but I prefer the one here. And then what we have here are different class representatives. So there are 239 images whose average is this image, and we can look at the individual images. So those are the images behind this class and supporting that class, and it doesn't mean that all of them really are exactly this one, and very often, especially depends on the data set again, but sometimes one of the classes has a very high signal to noise ratio, and then it attracts many other images that they don't really look like the class, but they have been attracted by this high signal to noise ratio. And we can also see that this is ferritin, apoferritin. So apo means without iron. So but some of the particles, they still have the iron inside, so not so many. So we see that the amount of particles with iron out of almost 3,000 something is 300. So it is about 10% of the particles had still the iron inside, maybe these ones too. But so what I did here was, so you choose the particles that have no iron inside. So all these classes, and maybe not this one, and then you create a new set of classes, a new set of averages, or a new set of particles, depending on what you want to do next. So the new set of particles is just the particles behind these classes. The averages are just these images, so the representatives. So if we have chosen here 30 averages, so we have just 30 images, and the classes is both. So it is the averages, those are the representatives, plus the particles that are behind them. So I chose the classes, and the reason is that I wanted later to recenter the particles. So for centering the particles, you need a set of classes, and you need to link them to some set of micrographs. And this recentering of the particles will allow us to compute better initial models, and also to remove duplicates. So for instance, here now we can have better estimates of what are the particles that are really or which are the coordinates that are really pointing to the same particle. And now we can look at this output, and in principle we shouldn't see those many overlapping particles. So you see that I cannot see anyone, and we can also see that by this 2D classification we have get rid of the particles with iron. Not all of them. This one has iron, this one has iron, and it was attracted by one of the images or one of the classes without iron. So this is a good example that not all the images supporting a class really is absolutely represented by that class average. So sometimes these algorithms also commit errors. It is interesting to see what are the particles in the low density peaked micrographs. So we see that we don't see badly peaked particles. So for instance, again, this one, probably here is a thicker area of the ice, and you can see this one too. So this is a pretty decent job. Okay, so this is our particle selection, and we have done it with multiple pickers, and then trying to find a consensus between all those pickers in a smart way with these deep learning algorithms. And then we have removed those, very few of them actually, 1%, but those were 1% that probably had some problem. And then getting rid of the classes we are not interested in through this first round of 2D classification. You can run multiple rounds of 2D classification. Sometimes it is useful, sometimes it is not so much. The first round was already giving a pretty good result. So this was the case in this example. We don't have those many particles, and actually all those particles, they seem to be pretty well chosen. Okay, so let's stop here, and we move on in the next video to the calculation of the initial volume.